was supposed to be talking about the 1144. Actually, I still am, but also I was anticipating 2 years ago when I submitted this abstract to talk about the 1111, lanthanum iron arsenic oxygen. There are several magnetic phases that we observe, and unfortunately, we need to remain focused on 1144, so I don't have the time for 1111. Let me see. Before I get started, I'd like to acknowledge my collaborators. Zahir Islam is actually the main author of many of these slides. He's the one who performed resonant resonant exchange X-ray scattering. We have a whole bunch of people at the Material Science Division, including Ulrich Welp Smiley, who did the magnetic measurements, and Kristen Will, I believe. I don't know her, but she works with them. Crystals are made by Jim K. Bao, as was mentioned earlier by Simon. These crystals are air sensitive, so usually to ship them from one place to another, we have to put them in evacuated ampoules and make sure they don't get exposed. We coat them with Cytop on site, and eventually that will get degraded over time. So definitely we need new crystals if anybody is interested in pursuing these materials. Jenkins right now is in China, so we can still talk to him, but he's the one who grew the crystals. We have Huibo Chow from Oak Ridge National Lab who performed with me the neutron diffraction experiment and confirmed the helical structure that's been already shown a few times. So the motivations you've heard that already many times. We've been hearing about coexistence of long-range ferromagnetic order with a huge magnetic moment, about 7 Bohr magneton, coexisting with superconductivity in 1144. For the first time you hear of this, you don't believe it, but then you start looking at the details. When you see how the helical structure is formed and the distance between the different layers, you start understanding what's going on. And Alex just made a great case for their coexistence together. So in any case, that was what motivated this work a few years ago. It's maybe 2.5 years ago. The other motivation was to look at use X-rays to look at magnetic order in these complex materials. Well, you know that X-rays are not extremely easy to use for magnetic determinations, but with resonant exchange scattering, this is actually possible. If you tune the energy to the Europium L2 edge around that much energy, you can get enhancement in the cross section and magnetic cross section and observe the magnetic peaks. The measurements were done on beamline 6ID, B, and C. Again, these are run by Zahir Islam. Neutron diffraction, as I said, was done with in collaboration with Hugo Chow at Oak Ridge National Lab at HIFER, this instrument HB3A. And I don't think I would be saying at this point we had determined a new structure, but magnetic structure, because it's been already shown a few times. But in any case, as you've seen already this slide many times, we have two transitions happening back to back. We start with the superconducting transition at 37 Kelvin, and then you have a magnetic order deep in the superconducting state. Basically, with bulk magnetization measurements, it will be masked, right? So you don't see it. You can't get to determine who is doing what. Now we know for sure iron sublattice is not magnetic, and europium is the one responsible for the magnetic properties. You've seen this already, that the easy plane in these materials have been determined by magnetization to be within the AB plane. The measurements that I will show you later prove this case, but again, there's many degenerate states, and it's really impossible to determine in which exact direction the magnetic moments lock in place. So it can be along the A-axis, the B-axis, or anywhere in between. They're all degenerate, and diffraction does not give you any way to discriminate this or that. So the crystal structure at room temperature is tetragonal with these lattice parameters, but then when you do the measurements at base temperature or high resolution X-rays or neutron, we see that it retains the same tetragonal symmetry and while preserving the rotational symmetry. See, the lattice parameters simply just contracted a little bit. This is the actual crystal that was measured with neutrons about 0.5 millimeter wide, 1.1 to 1.2 millimeter long. The thickness is about 40 microns, 37 or 38 microns. So it's a really small crystal, but we managed to get a decent number of magnetic peaks. Of course, we had to also measure nuclear peaks. We were able to do that within a few days at high pressure. It was actually quite successful. So first, with X-rays, the way the sample was mounted, as you see in the sketch here, you have the plane, scattering plane. Incoming X-rays are polarized horizontally. You have basically, in this technique, you have a pair of, basically an electron and an inner core orbital absorbing the incoming energy, getting excited to the valence band above the Fermi surface, then jumping back down, emitting a photon in the process. An emitted photon would have obviously different polarization. You can calculate the intensities of magnetic intensities that you would expect in different channels. In these equations here, you can see if you look at this channel here, K prime dotted with Zn. Zns are the unit vectors of the magnetic moment within the domains, the individual domains. So obviously you have to sum over all the domains. So you can see if you look at those equations, you see that I sigma pi and the intensity in the pi sigma channels, they are both sensitive to moments ordered within the scattering planes horizontally here, which means the moment can actually have a component in the c-axis because it can tilt in and out, right? While the pi channel, if you again do the math, you see it will be more sensitive to the to moments perpendicular to the scattering plane. So we can actually just analyzing using some analyzed crystal, pyrolytic graphite crystal usually. We can analyze in what direction is the polarized beam or emitted beam and figure out the direction of whether we have significant component in the out of plane direction or in plane direction. So we have a bunch of measurements here done in the vertical scattering geometry. That's basically focusing on the sigma pi channel. You can see, I don't know if you can read it in the room, in the hall there. So I mean, I can tell you we're starting from these are all 00L scans. We're looking at L equal 1, 2, 3, 4, 6, and 8. And you can see in the middle, the peaks are showing up at quarter values. This one like 1 1/4, 2 1/4, and so on. And likewise here, you can see them at 3/4 values. So you see those at really long, many Q values, and high Qs and low Q peaks are measured, and they indicate a Q vector of 0 quarter. So you can you immediately tell that there's a fourfold. I'll say the structure is 4 times larger along the c-axis, and that could suggest that we have staggered ordering. And basically, well, we still have to determine whether this is due to stacking force or not. But that was the first clue that we have. The fourfold superlattice. You can in the horizontal scattering plane without any analyzers, you combine both pi and pi sigma channels. You can see the same thing happening with different. They're all at quarter, 3/4, and so on. everywhere at very large Q values. Um, I cannot step here. Okay. Some scans here to show whether the material is really magnetic. I mean, I don't think I need to prove it anymore. It's been proven a few times before me, the previous couple of sessions. But still, it would be nice to show that we looked at, say, the 0011 and a quarter magnetic peak and did some analysis for its full width at half maximum. We saw it is, I'm running out of time, it seems like. We saw that it's actually quite sharp. The mosaicity is what you expect for a single, for a nice crystal. You can rule out by actually comparing it to a charge peak like 0012, we can rule out the formation of the magnetic origin as being due to inner growth or stacking force. So we know it is a long-range ordered magnetic structure, anti-ferromagnetic, because we have to double the structure along the c-axis 4 times. Well, not double it 4 times, but we have to increase the set by 4 times. X-ray measurements as a function of temperature shows the following this 2.75 peak. It shows that it dies off around 15 Kelvin. That's exactly where the magnetic transition happens. Neutron diffractions, I have a lot of scans, but it will be repetitive to show. But at least I'm showing here very similar magnetic peaks observed with neutron diffraction. These are purely magnetic in origin. But I mean, the reason obviously you see this more noisy peaks compared to X-rays is first because the crystal is too small, and we needed to run a lot of collect data on a lot of peaks, so we couldn't spend so much time on every single peak. All right, with that, we proved that we have interferomagnetic structure. We see it in different polarization channels. We confirmed it with neutrons. We can monitor the order parameter using a power law. The exponent of the power law comes out to be 0.29, which is in agreement with the three-dimensionality of the magnetic ordering. You can see here in this top panel that a charge peak 001 as a function, scanned as a function of energy, the response is what you would expect for these peaks. But if you were to scan the magnetic peak 002.75, for example, you have a huge increase in scattering at resonance. Again, this proves the magnetic property of this peak, especially when compared to a charge peak. Let me see. Really exactly.
Sorry, we have 5 minutes.
5 minutes, excellent.
Yeah,
Because I keep monitoring my time, that's taking away of my focus. This actually shows you the excellent agreement between neutron and X-rays, showing the order parameter scans. Blue, what is it? Neutron scattering is the magenta peaks. The blue is are extracted from resonant X-rays. There's nothing beyond that. I mean, this is a couple of peaks, nuclear peaks that were measured with neutrons, showing there's absolutely no things at the magnetic transition temperature. Only the ones that have a quarter or 3/4 characters are magnetic. The others are not. The next thing would be to integrate all the intensities in the different polarization channels and plot them versus Q for all the peaks. See how they what behavior they produce. If you look at the clustering of these integrated intensities, you see they follow this curve, which indicate that the magnetic moment of europium is within the AB plane. But again, we cannot pinpoint in what exact direction because they're all degenerate, and neutrons couldn't help us either. You point your magnetic moment in any direction, it works. You have exactly the same residual factors. But we can definitely rule out the magnetic moments along the c-axis, because you would expect the intensities to cluster along this dashed line rather than this one. The last thing I want to say here is that if you want to investigate the ferromagnetic character of the magnetic ordering, you obviously need to apply magnetic field. We apply it in this direction, perpendicular to the scattering plane. In this graph here, you can see the effect of magnetic field on a charge peak 0012. That peak was selected because its Bragg angle would basically produce a very low intensity. Of course, if you're probing ferromagnetic structures, that means the Q vector is 000, which coincides with the charge lattice, and it will be extremely hard to distinguish one from the other with X-rays. The way to do it is to find the peak where the Bragg angle scattering is like 90 degrees, so there would be no scattering roughly, and charge scattering. Everything would be close to magnetic. So when you apply a magnetic field in that direction, you can see the 0012 gaining some intensity. Even when you reverse the field, you can see that actually this is integrated intensity here. This is zero field, positive field, and a negative field. You can see there's gain due to ferromagnetic ordering on that peak. I'm not gonna follow this one, but I can maybe follow some magnetic peak, the 11 and a quarter peak, starting from zero field first. The intensity measured is at this point. You apply about 0.6 kilogauss field. You can suppress the anti-ferromagnetic order completely. Then if you reverse the magnetic field, you can recover it a little bit, as you can see here, going back and forth. There's some hysteresis here. Now you don't go back to the same intensity because some ferromagnetism remains locked in place. But if you were to warm the sample to above 15 Kelvin, you go to 30 or 40 Kelvin, you will recover that intensity. With that, I reach my conclusion. Well, actually, this is the structure that we've seen already, and the refinement results of the magnetic structure. So my conclusions, you've seen it already several times today, is that yes, we do confirm fourfold periodicity along the C-axis in the 1144 due to European magnetic ordering in a helical structure. And most importantly, we confirm that we can distinguish using X-ray resonance scattering. We can distinguish between charged peaks and magnetic peaks very neatly. That is actually something that has been gaining more popularity in recent years. With that, I'm gonna stop here taking any questions you have. And I realize I don't have much time, but I would love to answer your questions. Well, I'm not hearing any questions. I know that it's the end of the day in Turkey. We're still in morning here in Chicago, but in any case, being the last speaker, I thank all the speakers in this session, and thank you for your attendance. It's been a great day. Thank you again. What? There's something?
There is question in the chat.
Oh, we can't get these peaks unless they are at least a few hundred angstrom long. The peaks were quite strong, actually. As I showed you, the crystal was quite tiny. I think you showed it, Simon. You showed that particular crystal in your slide. So yeah, that was a very small crystal, and the peaks were observed within, I would say, minutes. So there's a lot of, we didn't have many twins in that crystal. Maybe there was a tiny twin. But I would say, based on experience with other samples, it would be at least 300 to 400 angstrom wide. Not smaller than that. Should be more, actually, because the peaks are quite sharp. There should be more. But I can't get a definite answer for how big they are. That's the only thing I can do with diffraction.